All right, everybody. Welcome to another episode of Tim Rambles On About Wine. This is kind of a fun one. I wanted to talk about two very different varieties and how, even on the surface, that basic juice chemistry can be a bit misleading, and we always need to learn a little bit more. So, why this is important is we want to talk about two things. First thing is we want to talk about juice chemistry to wine chemistry. So, what are the things we're looking at in a report that lead us to say, hey, here's what we're going to do to a wine and how do we get there? What's the thought process? What are the things that we're going to do in order to get a wine to where we need it to be? So I'm going to do winemaking 101, which is where you're at now. We're going to do juice chemistry to wine chemistry, and we're really going to focus very significantly on how acid works and how acid shifts. I think that's really important for you to see how that works. And then also talk about how we decide, water additions and things like that. So I think that's important. And then also I'm going to go all the way into kind of 401 for those that want to get a little bit higher order stuff about where we look at phenolics and we look at tannins and how we make some decisions in terms of oxygen management to get us from what's in the fruit to what's in the wine, maybe some of the decision making process along the way. And these wines couldn't possibly be more different. So without discussing anything more than that, I think we have to go with what the student goals were. What are they trying to get out of it? So we have to look at the two student groups. So the Tempranillo group was really led by Toby Turley, who's at Duclos Cellars, and then also I would say Joe Woodworth, who's in the dog shirt. They're with Alton Wines now. They were the big drivers, and of course Zach also in this. He was a huge influence as well, kind of a workhorse. But really it was Joe and Toby that were kind of you know masterminding this. And then we have Mary Robertson, Mary Delmas Robertson, who is with Delmas Wines down in the Rocks District. So a pretty interesting, fun group. And then the Malbec group on the right side I thought was really fun because it looks like Dad and the girls go camping. And that's Keith Knight, and he stepped in the program for a while, famous musician, and then moved on. But then Coco Chester, she was recently graduated, and then Lindsay Nurse, she's up at Ciel du Cheval Vineyard. But just a two great groups of people. But the Tempranillo group, what they wanted to do was make a little bit more of a serious Tempranillo. We'd always make these sort of flamboyant wines. So they wanted something with more tannin, more structure, more focus. And then the Malbec group wanted to make something just a beautifully pure Malbec. And we'll see if they accomplish their goals. So the thing is when we look at basic juice chemistry, these two wines are really pretty similar. So on the surface, we go, they're about 25 bricks each. That's going to make around a 14.5-ish% alcohol wine. So what the heck, ferment it. The pH isn't terrible. The Tempranillo's a little high. The Malbec's a little bit low, but not hugely different, but they're different. And the titratable acidity is a little bit different. But the thing is that these numbers are really misleading because pH in juice is really tricky, depends on the acid matrix and what's causing the pH to be a little bit higher on the Tempranillo versus the Malbec, even though their acids are moderately similar. And then why is that titratable acidity just so much different? So I think at the end of the day, we take a look at this and go, there's a lot more knowledge that we require. This just isn't enough data on the surface for us to make a really good production winemaking decision. So let's take a little bit deeper look underneath the surface to see if we can learn a little bit more. And so the first thing we look at is glucose plus fructose. So this is how much sugar is really in the wine. Remember, bricks is simply a measure of total soluble solids. It will tell you that a professional bodybuilder and somebody who's morbidly obese are the same because all it's doing is measuring weight. Professional bodybuilder, you put them on a scale, they're 6 foot tall, they weigh 330 pounds. The doc could say, hey, you're morbidly obese, but they're only 2% body fat. It's just telling you the weight of something. It doesn't tell you anything about what's really in the wine. So when we actually look at these numbers, we go, well, maybe we want to go ahead and make a little bit of a water adjustment on both of these. So in red wines, we basically say about 58% of our sugar gets converted into alcohol. So that shouldn't be 0.58. It should be, a factor of 0.58 or 58%. So that means we'll get converted into alcohol. So when we add that up, these are going to be a little bit higher. These are going to be in the 15% range if we don't do something. So we need to water these back. And in that water back process, we're going to add a bunch of acid to the Tempranillo, and we're not going to add any to the Malbec. And why is that? Well, again, we need to know more. and knowing is half the battle. So what about malic, tartaric, and potassium? So this is where we have to start looking at the whole picture. And I'll do this in a little bit of a graphic representation to make it a little bit easier. But we have two very different acid structures. These wines could not be more different in a textbook sense. So let's start with the first line, which is just malic acid. So the Tempranillo is malic acid dominant. That's the main acid in this wine. And then in the Malbec, the main acid is tartaric acid. It's about 6 grams per liter. These are very inverted. And the reason for that is primarily variety dependent. It just seems to be what happened in our vineyard. The Tempranillo is now gone, so you don't have to worry about that anymore. But we know that some things are going to happen. The other thing we want to look at here is that potassium number. And you've heard me talk about potassium before. Potassium is the primary thing that causes wine to be buffered, grape juice to be buffered. That means it keeps the pH from shifting down no matter how much acid is in it. So the thing is in the Tempranillo, we have a lot more potassium. That's going to cause greater buffering. That's why that pH is higher in that wine. And then there's another concept I want to bring to you is something called isoelectric point. Is that when your pH is above around 3.6, when the potassium takes the tartaric acid out, the pH will shift up even when you lose acid. So you're going to lose acid, and if that pH is above 3.6, the pH is going to go up. But what's really weird is when it's below 3.6, when that potassium precipitates out, the pH actually drops. And so this is something we'll talk about more in the future, but that gives us a lot of things about our decision-making matrix that's going to happen. So the Malbec was below 3.6, the Tempranillo was above. So we would expect that pH shift to be a lot more dramatic in the Tempranillo as we move on. Again, I'm going to show you some graphs on this, so that should help out a little bit. So the things that we can anticipate is that in the Tempranillo, that tartaric is going to precipitate out, our pH is going to go up, and then malolactic fermentation, that malic acid is going to disappear by half. It's going to go away. So there's a sort of double whammy effect that's going to happen in the Tempranillo where that pH is going to shift pretty dramatically. Whereas the Malbec, because we're low, our tartaric acid is our dominant, and our pH is already low, we're going to expect somewhat of a pH shift, but nothing nearly to the effect of the Tempranillo because we just don't have as much malic acid to convert, and we just don't have as much potassium precipitate. So we don't really need to do anything to this wine. So if we were to look at these, back up to that slide where you're looking at just titratable acidity, you might say that neither of these need acid, but it's pretty apparent that the Tempranillo is going to need some sort of an addition. Even then, we're going to have some crazy things happen. So let's put this in some graphic representation. So let's visualize how acid shifts. So what I like to do is think of total acidity. We talk about TA, and TA is titratable acidity. That's just how much we can titrate with a base versus a known strength base against an acid. That's why we call it titratable acidity. But when we actually do some enzymatics and look at what the acids are in the juice and add it up, we actually have quite a bit of acid in these wines. We talk about these racy acid Rieslings at around 9 grams a liter, and we're sitting on these numbers with both of these wines. So take a look at the Tempranillos, over 9 grams a liter and well over 10 with that Malbec. But the species of acid are very different. So let's talk about that and let's walk through the things that are going to happen. So the first thing that happens is potassium bitartrate precipitation. This is where the potassium that's in the wine is going to hook up with the tartaric acid in the wine. Potassium and tartaric acid become friends, and when they become friends, they precipitate out to the bottom of the tank as cream of tartar. Potassium bitartrate, it's like the crystals in the bottom of the container. You've heard me talk about this before. We'll talk about it again. So we're gonna have that first shift, and that first shift actually happens really early on. As soon as we crush the grapes and the potassium is interaction with the acid, there's going to be precipitation. Remember, it doesn't react with malic; it only reacts with tartaric, and that precipitation starts to happen the second we crush the fruit. Now, there's another thing that happens is as we ferment and that alcohol content goes up, the potassium bitartrate becomes less soluble. That means more is going to fall out as fermentation goes on. So as we're doing our punch downs, as we're reintroducing the potassium that's in the skins to the acid that's in the pulp, we're going to have that happen. That precipitation is going to be happening. And then as ethanol rises, that's going to cause more and more of that to precipitate. As a general rule, I say most wines can carry around 700 milligrams a liter of potassium. So whatever we have in excess of that is going to precipitate out tartaric acid. So my first thing that I look at is how much tartaric acid do we have how much potassium did we have, and how much is going to precipitate. So right after that first precipitation event that happens during fermentation, and that'll also continue to happen throughout the life of the wine and through cold stability, but primarily it happens early on. Our first acid shift is going to move that Tempranillo down into a sub 8 gram per liter range. So we're already down in the high sevens, which is moving into red wine range. And then the Malbec has a smaller shift, but still well above 9. So we've got plenty of acid there. So that's the first shift that happens. That's our first thing that we look at. Well, then our next shift happens. And this is the big one. And this one's going to be really dramatic on that Tempranillo. So basically, for all intents and purposes, malic acid gets chopped in half and gets turned into lactic acid. And so, this is from Wine Folly. So thanks, Madeline, for this little graphic here. Basically, you have this little bacteria called Anthocyanin that eats malic acid, turns it into lactic acid. Malic acid is a relatively strong weak acid. I know that sounds crazy, but it has got two protons that it can donate to solution to drop the pH, which is cool. No quiz on this later, trust me on this. But it's got two that it can donate. And then lactic acid only has one. And good old Enococcus chops off one and kicks it off as carbon dioxide, and then it makes the acid weaker. So not only do we have less acid, we have a weaker acid. So we now see after this precipitation event that we had, originally potassium bitartrate, we've reduced the acid. Now we're going to take it through malolactic fermentation. And because there's so much malic in the Tempranillo, we've gone from a 9+ gram a liter wine down to a sub 5 gram a liter wine. And that's just fat, super fat. Whereas on the Malbec, take a look at that. There wasn't much malic to begin with. So the conversion and the shift isn't going to be as substantial. And if you take a look at that, it's pretty obvious that we're now at a almost 8 gram a liter wine, so 7.5. But still, a 7.5 gram a liter red wine is pretty puckery. So we're going to say we need to do some work here. So let's go ahead and talk about the thought process that goes through to make some additional steps. So now we've got to decide whether we want to add acid or reduce acid. So in this case, the Tempranillo, we went ahead and added 0.5 gram a liter of acid. I think we could have added more, but we just didn't really want to overdo it. So we did add a little bit of acid to the Tempranillo. So not only did we do water back, we added acid. Whereas the Malbec, we knew we had plenty of acid to begin with. So when we watered back to get the alcohol down, we just didn't add any acid. We just diluted the acidity a little bit. And so our estimation of our final wine titratable acidity is that Tempranillo should be a little over 5.5 grams a liter, which is still on the fat side, but reasonable. The Malbec is going to be around 6.5 grams a liter, which is pretty classic, Cahors Malbec territory. That's right out Argentina. That's right where you want to be, is that mid 6.5 range. And that's a pretty sweet spot to be. But you think when you taste these wines, you'll be able to see that difference in acidity pretty significantly. So how did it work? Well, here's our estimation, and this is what the math says will work. And then here's where we really ended up. And we ended up with 5.3 and 6.7 grams a liter of tartaric of TA in the wine. Now, TA is, you've heard me say in juice, is terrible. It's an awful measurement. But in wine, it's actually pretty solid. Once we have finished wine, we've got all the potassium that's precipitated out of the way. We got all the sugar and everything else that can muck up that measurement out of the way. It's really correlated with how we perceive the wine to taste. So in this particular instance, we go, wow, this is right about where we wanted to end up. The Malbec may have been able to come down a little bit, but I think, depending on the food you're going to have it with, it's really nice. It's got some good acidity. Whereas the Tempranillo, on the other hand, it's definitely got that width and breadth of weight on your palate. So this is that idea of how does acid shift in wine? So if we were to, kind of look at those original numbers, we want to go back and say, what's the decision-making process to get us where we're at now? And that Tempranillo definitely needed an acid addition. We may have been able to add a little bit more in hindsight, but this is why we do what we do, and we continue to take data and we continue to record. And the Malbec, we could also, make some decisions on whether we wanted to, maybe deacidify a little bit if we wanted to go for a little bit different style as we move forward. But as the Malbec group will attest to, we looked at the numbers, we said we don't have to do anything, so we just let it ride. So in some years you just get to do that, but sometimes you've got to make adjustments. So, even though acid and pH are somewhat related, I think it's important to talk about pH. Now, pH in wine is really, really important. And why pH is important is the lower the pH is, the harder it is for things to grow in it. To give you an idea why it's so important is that something at pH 3.9, no matter pretty much what it is, whatever fruit it is or anything like that, you probably can eat it without getting sick. pH 3.9 is unlikely to allow listeria or botulism to grow in it. Whereas once you get over 4.0, you start to run into some bad actors that can live in it. And even though it seems like a really small difference in a number in and of itself, the difference between a pH of 3.8, 3.9, 4.0 is pretty substantial in the microbial world. Microbes, that's the difference between living in 80 versus 100 versus 120 degree weather to humans. I mean, it's a very significant difference. So, so don't take those numbers lightly. And why that's important is that the number of bad actors that can come live in your wine goes up significantly as soon as you move up 3.6, 3.7, 3.8. There's a lot more bacteria that can come and live and move into the wine. So it's really important that you manage your wine a lot more significantly when you start working in these higher pH wines. Now, botulism and listeria obviously can't live in wine because we have alcohol in the matrix, but there are other microbes that can come along. So pH is very strongly correlated with spoilage organisms and things going wrong in your wine. The higher the pH is, the more things you're going to fight and the bigger challenges you're going to have. Additionally, pH is very, very important for sulfur dioxide. And basically, sulfur dioxide becomes more and more effective at lower pH. It turns into a gas at low pH, and that gas is what goes into the cells it penetrates the cell membrane of different microbes and is able to cause them to become really quite sick and die and become ineffective. So low pH is really important also for the efficacy of SO2. So both of those things together are really, really important to talk about. So let's talk about our pH. And so let's look at our pH of our incoming juice. So our Tempranillo wasn't all that bad to begin with. And here's our Tempranillo wine. Pretty significant difference when we see how that shift happens. So we went from pH 3.7 in the juice to pH 4.16 in the wine. So we have gone from a wine that's, would be normal to a really high pH wine. And pH 4.16 is a crazy number, whereas the Malbec is like spot on. That is textbook pH 3.65 in a red wine. You couldn't write a better script. It's beautiful. And to that I say, holy shit, dude. So here's the current wine chemistry on these two. We were shooting for 14.5% alcohol. The ethanol in Tempranillo is 14.56 versus 14.71 on the Malbec. And our pHs are perfect. And the titratable acidities are about where they should be. It's a low for the Tempranillo, but the titratable acidity for the Malbec is just perfectly moderate. And then we look at VA. VA on Tempranillo, 0.59 grams a liter, is still low in the grand scheme of things, but the Malbec is ludicrously low. At 0.34 grams a liter. It's one of the lowest red wine VAs I've ever seen. And I just attribute that to a very moderate amount of malolactic fermentation and just a really clean, well-moderated ferment, because they wanted to really go for fruitiness. They didn't want to withhold any nutrient. So we gave it everything it needed, and it powered right through ferment and just ended up with a really super clean ferment. So let's talk about tannin. Again, everything happens in the vineyard. I want to keep beating you over the head on this. Canopy management is a big thing. Leaf removal and timing is really important. Also, abusing your fruit. So high tannin sites frequently have high wind, and the grapes get abused. So between sunshine and just getting whipped around, those all cause tannins and phenolics to increase. And also, the longer you hang the fruit out,
the more the tannin's going to go up. And remember, tannin's a big mishmash of stuff. So the longer you hang it, there's some oxidative things that start happening, oxygen management literally in the fruit as it's hanging out and oxidizing and starting to shrivel a little bit. You're going to get more tannin just due to that oxidation that's happening in the fruit sitting out there. Other things we can do is do stem inclusion or removal. Those impact tannin quite a bit. When we get into experimental wines next week, we'll talk about that. Another thing you can do if you want to have a little more tannin is do a saignée, which is a bleed. Take some juice out. If you've got a vineyard site that tends to be a little bit weak, and make some rosé out of it. Other things that are big drivers are the temperature of the fermentation or temperature of just the cap or the must. And again, the Tempranillo, we did the cold ferment with a hot extract. And then the ethanol content of a wine also helps hold tannin into solution. Enzymes and adding enzymes has an impact. They will help extract more if you add extraction enzymes, and also length of time on skins. And about length of time on skins, one thing I want to mention is it isn't linear how much tannin you continue to extract. You kind of reach a peak, usually somewhere between 5 and probably 15 days. And then after that, the tannins begin to sort of polymerize and fall out. There's been a lot of research on that. And either they polymerize and fall out, or sort of because the yeast and everything are still in suspension, you have sort of a self-fining effect with those yeast pulling tannin out. But you do get kind of peak extraction after only a number of series of days. And then after that, you'll actually start to have a precipitation event. So let's talk about the tannin that we had and what we brought in. So the Tempranillo has plenty. So when we brought it in, we were looking at a lot in the Tempranillo, and we knew we wanted to extract enough to taste, but we didn't want to go too over the top. So we had to be really careful with how much we brought in. But again, then the Malbec, on the other hand, is really moderate. But the good news is with the Malbec, we're going to have a little bit more acidity to enhance tannin perception. Whereas the Tempranillo, we know we got low acid, so we can probably push those tannin numbers up just a little bit. So approaches to managing tannin, we did these very differently. So the Tempranillo, we did a cold soak first to get as much color as we could because it was a low color variety. We had lots of tannin, but very moderate color. I'll get onto that in a minute. We did a destem only. We did a slow, cool fermentation. We did punch downs just once a day. And then post-primary fermentation, we heated it and we kept measuring extraction by taste. And then we basket pressed it in order to make sure that we didn't over extract it. We were really gentle on it. Whereas Malbec was straightforward, nothing fancy. We destemmed it, we crushed it, we fermented it 8 days on skins. We didn't do punch downs on it. We just did simple pump overs. And then right afterwards, we just pressed it in the bladder press, and it was as keep it simple, stupid as you can ever expect. So I want to talk about catechin. We've talked about this before, but this is that indication that that there's a lignification of seeds. Catechin is high early in the season, and then as the fruit hangs out longer and longer, catechin continues to go down, and it's just an indicator of seed ripeness. There's many other factors involved, but it doesn't just go down. It's just getting knitted up and turned into tannin. So it's in the highest quantities in seeds and stems, and our way of managing it is through canopy management in the vineyard, leaf stripping and shoot thinning. And then also another thing that plays a role into catechin development is just moderating your crop load to keep it down. And another thing that's interesting is older vines tend to produce more catechin, all things being equal. So they tend to not get the seed quite as ripe. And that's one thing we did a study a while ago, and we did vine age, we did Cabernet all over the state. And the one thing that increased pretty linearly was that catechin went up. And so catechin is a seediness, it gives wine a dustiness. And I think maybe it's what gives that notion that old vines give more structure to the wine. And it's the older the vine gets, the harder time it has kind of knitting up all those tannins later on. But again, every variety is very, very different. So let's take a look at these, and I just want to throw them out there. There's not much to begin with in either of these. There wasn't a whole lot in the Tempranillo, and then we just ended up with less in the wine, and we tend to see that because the catechin will tend to knit up with other stuff. But the Malbec I thought was pretty interesting because we had so many anthocyanins, and anthocyanins are so reactive that I think the anthocyanins and catechins reacted to make some more polymeric anthocyanins. So we see that big reduction in the Malbec. So these are things we want to talk about. And this is where things get rubber really meets the road is with anthocyanins. So Malbec is already known to have large quantities of anthocyanins. It's probably one of the reddest varieties I've ever seen. I very rarely see anything that has numbers as high as the Malbec. Tempranillo is a little different beast. It has moderate amounts. It's a fairly high tannin variety, but only moderately colored. And so these anthocyanins are produced in response to early sun exposure during berry set, so leaf stripping around berry set, and then again canopy management. And another thing that it also impacts anthocyanins is nutrient. If you put a lot of fertilizer on your plants in an attempt to get your yans up, in that process you will cause your grapes to have less anthocyanins. So it's a trade-off that you kind of have to go through. So our goal in any case is to have our peak anthocyanin development coincide with sugar, acid, and tannin ripeness. So have all of these things line up that you get your peak anthocyanins, and that's when you pick, because that's when you have the most highly reactive material to go in and polymerize and build your tannin structure. So let's take a look at these two. In the case of the Tempranillo, we only had a moderate amount. As a matter of fact, what we generally want to see is at least, I like to see 2 to 1, 2 parts of anthocyanins to 1 part tannin. And in the Tempranillo, we were close to 1 to 1, about 1.5 to 1. And so that's a challenge because you've got all the tannin in the world, but it's going to be really tough to polymerize. That one's going to end up, no matter what we do, probably pretty dusty unless we were to just not extract it hardly at all and gone for a lighter style. But that wasn't the group's goal. They wanted to make a wine that would age and last because it's our last Tempranillo we're going to make. We wanted to make it haul as long as we could. Whereas the Malbec, we had tons of color, super colorful. And so we want to see where they go. And so here's where they were in the fruit, and here's where they are in the wine. Now remember, they're very labile compounds. And so what we see is a reduction in them pretty significantly. So they're going to diminish rapidly. So what we started with in the beginning, we ended up with a lot less. And I think the Tempranillo wine, the reason why they're as high as they are in the Tempranillo wine was that, cold soak up front and just every attempt that we had to maintain anthocyanins as good as we could, in regards to extraction. Whereas the Malbec, we had plenty of color and we moxed it and we wanted to make sure that it got all knitted up. So I want to do a quick detour on pH and anthocyanins. So take those 2 glasses and hold them up. And, we've heard me talk about this before, but I think this is a really good opportunity to see how pH affects your color. Because, we really aren't differing a whole lot. There's a little, a fair amount more anthocyanins in the Malbec still, maybe 20% or so. But the big difference is look at the difference in color. That Malbec is fluorescent almost. It's iridescent because that pH is sitting right on that 3.6 number, which is that bright red range where we've got a little, not bright red range, but more in that flavilium form, where we've got just this really beautiful red color. Whereas the Tempranillo is much higher. And the quinodal form, the violet form of anthocyanin, is not as brightly colored and it's just not as colored. So I think the Tempranillo, you actually can look at it, you can see the tannin. It's almost brown. You'll see that more brownish hue, and that's just simply tannin. Tannin's brown. It's a big knitted up pile of stuff, just like a seed, brown seed in the grape. So you see that shift, and then you'll also see how pH, when you get these high pH wines, not only do they aren't quite as colorful, but if they're high tannin, you get more into that auburn hue. So pretty cool.
So let's talk about polymeric anthocyanins. Polymeric anthocyanins are associated with tannin through a complex set of reactions. So basically, polymeric anthocyanins are anthocyanins that are polymerized to something. That means they're glued to something. That means we've taken anthocyanins, there's a whole bunch of them, they're floating around, and we stick them to something. And how do we stick them to something? Well, we can stick them to something, usually through, oxygen, where we chemically oxidize ethanol into acetaldehyde, or we use yeast that make a lot of acetaldehyde. Not all yeast make it, but some yeast make a little bit more. So we can either do it through oxygen, so those macro-oxygenations and meso-oxygenations, and then we can even micro-ox if we need to, where we add a little bit of oxygen to the wine in really tiny doses that will drive that ethanol into acetaldehyde, and then basically we're making tannin glue. So we're just gluing on anthocyanins to our tannins, and not only are we stabilizing the color, but then we're also polishing up those tannins. So the thing that's important here is that the degree of modification, how much polymerization there is correlated with astringency. So the more modified, the higher the number of polymeric anthocyanins in relation to tannin. That tells us how astringent a wine is going to be. So this is really just going to take what you're tasting in your glass and give you a very real way of tasting and giving you some empirical data to back up what you're tasting.
So here we go. Let's talk about what we did. So the Tempranillo, we did everything. Cryomaceration, dry ice addition up front, 4-day cold soak, cool fermentation with macro-ox. Then we heated it to post-primary fermentation. We basket pressed it. We meso-oxed it post-pressing, and then we micro-oxed it as good as we could with our tools. But we did hold it for 3 weeks in the barrel room, cool, and added a little bit of meso-ox to it every day in our best ability to go ahead and see what kind of polymerization we could get. And so I think all of those steps really worked, because we took a wine that didn't have a whole lot of anthocyanins to begin with, and we got all of them out. And then through working really, really hard at every step, we were able to polymerize that as much as we could. But that number is pretty small when you start to think about the ratio of actual tannin. But in Malbec, we just kind of made it. We macro-oxed it during ferment, we pumped it over, and then we pressed it before dryness. We pressed it early. So we were trying to make a silky smooth wine, and we definitely got a little bit more, some good polymeric anthocyanins. We could have made unlimited supply had we have wanted to, but we wanted to have it in line with the amount of tannin in there. We didn't want to make it just overtly polymerized, so it's just a big fat thing on your palate. You wanted to have some weight of tannin there. So we were looking to get that a nicely balanced wine. So we just didn't push it too hard. It doesn't say that there was a meso-ox on it, but I think we meso-oxed it a couple times in barrel, just as a general principle, but not too much, just a pretty hands-off approach. So this is where we want to talk about the plushness index. And so the aggressive polymerization on Tempranillo yielded pretty good results. 0.74 is not overtly terribly astringent, considering we're sitting on close to 1,000 milligrams a liter of tannin, 850 or something like that. That is pretty significant. So this wine should be a little bit dusty and things like that. The Malbec, on the other hand, is really, really polymerized. 0.9 is smooth as it gets. I mean, that is smooth in terms of a ratio. You get up around 1 on that polymeric anthocyanin tannin ratio, and you're going to have a really, really rounded wine. But what we want to talk about here is that sort of perception. The Tempranillo is probably going to taste a little bit dusty, but fortunately the acid's low, that it's probably not overtly in your face. The Malbec probably still tastes like it's got some good tannin to it, even though it doesn't have a whole lot, because of that where acid goes into influencing the way that we sense astringency with tannin. So pretty cool experiment. So here, let's do a takeaway on this. So Tempranillo, we had high tannin wine with only moderate anthocyanin content. That's a really tricky wine to make. So we did a really aggressive approach to polymerizing using oxygen. And then that low acid helps bring that tannin structure into balance. Malbec, on the other hand, we didn't have to worry about anything. It was just there. The anthocyanins were 3 to 1. Didn't have to do anything. It was going to happen naturally. Just let her rip. So we had everything to do to just make the wine. And then that higher acid will bring that perception of tannin and weight. I think it's probably, both of these are probably a little out of whack right now. The Tempranillo's a little knock-kneed because it's not even a year old yet. And then the Malbec, on the other hand, is also probably similar, where the acid's really kind of showing right this minute. And that'll kind of work its way through and step back as time goes on. But pretty cool. This is a way to problem solve, approach, and use all the data available to make wine. And so if you were to just get the basic chemistry on that Tempranillo and you'd never worked with that vineyard before, you could have mucked that wine up pretty good. On the other hand, the Malbec, you probably could have just made it. You didn't need anything but PHTA and Brix because the fruit was so good. You just nailed it. So this is one of those things where some winemakers think they're amazing because they just get great fruit all the time and make wine out of it, and everything's been done for them in the vineyard. They just buy from that vineyard that produces, you know, great fruit year in, year out. Whereas sometimes you've got to work it a little bit, and knowing is half the battle. And that's all, folks. That's practical juice to wine chemistry and then oxygen management all the way through. Hopefully those wines are showing well for you.